Greetings and welcome, friends. 10.3, using chords. Chords? Cohortes. Recall that a chord is a segment with endpoints on a circle. Because its endpoints lie on the circle, any chord divides the circle into, Jack, 2 arcs. I think you can imagine that. All right, so every chord divides a circle into 2 arcs. A diameter will divide a circle into 2 semicircles. Shh, gentlemen. And any other chord will divide a circle into a minor arc and a major arc. So, here's a few theorems for you. Congruent corresponding chords theorem. In the same circle or incongruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. So if you imagine connecting the endpoints of a chord, that results in an arc that is congruent, like so, or vice versa. If and only if, so this is biconditionally true. If I have 2 congruent arcs, then the chords that connect their endpoints will also be congruent. Makes sense? All right, talk to me after, or just mention it in the comments of this video below. Okay, there you go. Yes. On that previous one? No, it's not. Yes. Shh. Isaiah, quiet, please. They are on, that's where the limit is, the same circle or incongruent circles. So right, you are correct. You are correct. Yep. You are correct. And that's actually a really valid point. If I had a larger circle and then had this length and mapped it onto this larger circle, right? Even though the segments are the same, this arc is actually closer to the segment than this one is, and therefore this arc would be longer than that arc. Nope, it's starting with the assumption that you're on the same circle or congruent circles. All right, perpendicular chord bisector theorem. Oh boy, if the diameter of a chord is perpendicular, if the diameter of a circle, so I know it's a diameter, that right? You see the center plotted there, is perpendicular to a chord, then the diameter bisects the chord and its arc. All right? And then the converse is also true. If one chord of a circle is a perpendicular bisector of another chord, then the first chord is its diameter. So I could prove diameterness because it's the perpendicular bisector of a chord. And this theorem okay, I didn't know specifically which part you were referring to, so I don't know. It all worked out. Let's see, example 1. Let's cruise through these today. Don't you guys love circles? Circles. All right, example 1, using congruent chords. In the diagram, circle P is congruent to circle Q, FG is congruent to JK, and the measure of arc, JK, is 80 degrees. Find the measure of arc FG. 80 degrees. Done. I'm going to switch back to yellow now, just because that's my classic. Even though yellow is not my favorite color. Oh, true fans of Waddy Math would know my favorite color. You'll just have to wait until Reddit's Ask Me Anything coming later this month. It's not coming. I'm never doing that. But yeah, I should just do an Ask Me Anything about my favorite color, which of course is orange. Yes. Using a diameter. All right, so according to the sketch, because this point is plotted, it is, that's how we imply that it is in fact the center of the circle. So JL is a diameter. It says find HK. If NK is 7, then HN is 7, and HK is going to equal 14. and find the measure of HK, the arc, well, I know that this arc and this arc are congruent because that diameter is perpendicular bisector of the chord, and therefore 11x is going to equal to x plus 70, and I will subtract x from both sides. Oh yeah, you guys see where this is going. 10x is equal to 70. You guys already had the answer moments ago. Let's see, divide both sides by 10, because you guys are algebraticians, not just geometricians. X is equal to, there's a better equal sign, 7. Bam. I like it. However, they wanted the measure of HK. Huh. How do I find that? Wait a minute. Wait a minute. All right. I was worried that these were not in degrees, and that's why I was like, uh-oh. That's how am I going to revert back to degrees? That'll be tricky. But those are degrees. All right. So I'll do 11 times 7 plus 70 plus 7. Right, so that's 77 plus 77. Looks like 154 degrees is the measure of HK. The arc. So there you go. Those are in degrees. Eventually, you guys will actually talk about arc length. And that's what I thought we were doing. And I was like, uh-oh, we are not prepared, is what Illidan Storm Rage would tell us. No one knows my World of Warcraft reference. That's fine. All right, there we... Hey, represent! Wow. Wow, is what I should say. Using perpendicular bisectors. Check this out. 3 bushes are arranged in a garden as shown. Now check this out. Where should you place a sprinkler so that each bush is equidistant from the sprinkler? So if you imagine, now this is pretty cool. This is a good trick. All right, so there's those segments. Let's see. My circle tool is going to be an ellipse. How embarrassing. Nah, it doesn't matter. We don't care about flowers. All right, here we go. So watch this. I'm going to draw perpendicular bisectors to these. All right. If I want a sprinkler that is the same distance from each of those, then those 3 bushes would lie on a circle in which the radius is that distance and the sprinkler is at the center. In order to construct perpendicular bisectors, I'm going to do this. And let's see, I'm going to need it a little bit larger for this one. Tell you what, I'll do a different color here. Perpendicular bisectors. All right, and watch what happens here. Now, if a chord, let me ask you this, is a perpendicular bisector of another chord, what is that first chord that I mentioned? All right, this blue chord is a perpendicular bisector of the red chord, and therefore this blue chord will pass through the diameter of the circle. Now, if I construct 2 diameters of the same circle, their intersection will be what? The center of that circle. All right, so here's 2 diameters. Let's see if my circle tool, let's see, and if I scale this up, theoretically, all 3 should land on the same, what's the color I need? I have no idea. But either way, if you place your sprinkler at this point, it will be equidistant from all of those because they would be points on the circle, and that would be the center of the circle, and that distance would be radii, like so. So guys, because I knew that these were both perpendicular bisectors and they intersected, the only place diameters intersect in a circle is at a center. It's a good problem right there. It's a really good problem. I'll show you another variation of that from our blue geometry book that's like 12 years old. In a moment. At the end of the lesson, I will. Equidistant chords theorem. All right, guys, let's think through this. Gentlemen, right? You with me? In the same circle or in congruent circles, two chords are congruent if and only if they are equidistant from the center. Okay, so here's the idea. If these are the same distances, then these chords are also congruent to one another. All right, don't worry about it, Joshua. So the chords, now when I measure the distance from a segment to a point, notice we always would measure that distance perpendicular to the point. Okay, so let's put this to use in example 4. Example 4. That's right. Here, let's see. So in the diagram, QR is equal to ST is equal to 16. Right? So Tyler, this is 16 and this is 16. All right? CU is equal to 2x, already labeled, and CV is equal to 5x minus 9. Labeled as well. It says find the radius of circle C. This one's a good problem. Now, this orange segment and this blue segment, what do you think is going to be true? They are congruent to each other because these chords are congruent in the same circle, and therefore they are equidistant from the center. So I could say that 5x minus 9 is equal to 2x by def of Cong because those are congruent to one another. Let's see, subtract 2x from both sides. Tell you what, I'll add 9 to both sides at the same time. Right, Ty? We're going to get 3x is equal to 9. Divide both sides by 3. And I get x equals 3. Now, I think the more interesting part of this problem is yet to come. So if this is 2x, that means UC is going to equal 2 times 3, which is 6. All right? Now, how's this going to help me find the radius? Now watch this. No. All right. This distance is a radius, and that is the one that's drawn, but that is not the one that I want to work with. There's ways that I theoretically could do that. What about this radius? That's the same distance, right? You guys agree? Those are both radii. And I now know that this 2x length, UC is equal to 6. What's this length? UR 8. This is a right triangle. Hey, that's a variation of a 3, 4, 5 multiplied by 2, so this is going to be 10. The radius is 10. Or you could have just done Pythagorean theorem, 6 squared plus 8 squared equals c squared. But yeah, the idea of swinging the radius around to get that right triangle, that's going to be your easiest route. I don't even want to think about it. Because I don't know. I'd have to find this distance. Yeah, I don't know. I don't even know. There's probably another way we could do it. Maybe I could have found this angle using tangents. I don't know, guys. Maybe you can find an alternative solution. Let's see. I think, let's see. Last problem I want to show you. Avalanche Rescue Beacon. My younger brother's actually, he lives out in Juneau, Alaska. He just finished, I think, a course on like wilderness rescue. And I'm assuming avalanches are included in that. All right. You don't. So just follow along. An avalanche rescue beacon is a small device carried by backcountry skiers that gives off a signal that can be picked up only within a circle of a certain radius. During a practice drill, ski patrol, I'm glad they told us it was practice, so like we can all relax right now. Oh, okay. All right. A ski patrol uses steps similar to the following to locate a beacon buried in the snow. All right, watch what they do. I actually think I have a written example of mine doing this on my channel already, but not a duplicate of this problem. All right, here we go. This is what they do. The person buried in the avalanche, they have a beacon, and it's sending out a circular signal, right? When it reaches the limit of its signal, it would be the boundary of a circle. When you have your detector, all right, you would detect signal at some point. You're like walking around with a detector and suddenly you hear beep, 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 right? And then you walk across the circle and you're hearing beep, 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 and then silence. And so you would flag those 2 points like so. You would then find the midpoint of that, all right, just measuring out your paces, and then go perpendicular to it. And I don't know if I'm going perpendicular through the long way or the short way, but I would keep walking until, right, I'm hearing beep, 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 and then no more beeping, and I mark that point. And now if I turn around and walk in the other direction, beep, 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 lose signal over here, this now I know is a diameter, and if I find the midpoint of that, that is where I should start digging. All right? Well, whether you counted out your paces and then divided by 2, like if this was 30 paces and then you're like, okay, so I'm going to walk backwards on the same path, 15 paces, right? And then that's where you'd start digging. So there you go. So internet friends, you're welcome. I saved your life. Or your friend's life who was buried in an avalanche. Bye-bye.